So in the last class regarding the Newtonian potential, we have seen that in general continuity is not enough to solve the problem, potential theory problem, mainly Laplacian of u equal to f. And what we are going to see now, when f has a good smoothness like c1 of omega bar, then the Vx defined there actually defines the, it gives you the potential, so it gives the solution, so you can solve your thing. So we have defined the, let me recall that before going further, that one, your Vx, where is our Vx is defined, is not seen here, maybe Vx is defined. This is the Newtonian potential defined in terms of that. So let me recall first the Newtonian potential Vx, and then we will show that if you have enough smoothness, so Newtonian potential Vx equal to integral over omega phi of x minus y f of y dy. So we recall once again. So let me state the theorem and prove it today. So that's the first job, to prove this thing. So here is the theorem. Let f is in c1 of omega bar, where omega is bounded open in R. Then V defined as above, then V defined as above satisfies V is in C2 of omega intersection C1 of omega bar, so you and La minus Laplacian of V. So we will not discuss the boundary condition, which we will do it later. What we are saying that it satisfies the Poisson equation. So this is the Poisson equation. As we know that the difficulty is taking the second derivative. So first derivative you don't have problem, because the d phi and d phi by dxi are locally integrable. But then to take a second derivative, it's not allowed, because d square phi by dxi dxj is not locally integrable. So that's what we need to do, a bit of finer analysis. So that local integrability, lack of local integrability of the second derivative compensated by the regularity of f. Okay. So let me give you a proof of this. Proof is interesting. So you compute this. So taking derivative inside, as I said, is not a big issue. Okay, dv by dxi I can take inside. Okay, because this is locally integrable, which we have already seen in the last class, how to take the derivative here, x minus y f of y dy. Okay. Now what we do here, you do an integration by parts, because f is a c1 function. You can take this derivative d by dxi to the other side. So you can immediately, so with a minus sign, you have phi of x minus y df by dxi. This you could do it only because f is a c1 function. And then there will be a boundary term. We'll have a boundary term minus df by dy. Okay, no, there is a minor problem here. This is an xi, this is a y variable, so you have to be a bit careful in that. You have to change the variable first before doing this integration. So you want a differentiation with respect to y, because f is a function of, so of course this is a symmetry, you have it's a modulus thing. Phi is a modulus function, so I can change this function with respect to y, but when I change with respect to that function with respect to y, you will have dy into x minus y. So because if I change this with respect to y, a minus sign will be picked up. So you do this. Now do the integration by parts. So this is equal to integration by parts. The divergence theorem. You apply divergence theorem because minus will become phi of x minus y. These are all in omega. So you can do this omega df by dxi. And then there will be a boundary term. So that will an external normal derivative f of x minus y, f of y, nu I. This is the corresponding outward, nu is the outward unit normal, which are all you have done many times, outward unit normal. Okay, and this is over d sigma y. This is our boundary of omega. Okay, and I call this is an integral I1, and this is, I call it I2. So before proceeding further, let me make some remark. I will make continue here, but I want to make some remark, and it's also an exercise, remark and exercise. The I2, this is I2 term. I2 I will call it as a new function. Okay, so I2, which is a function of, this is called some, say, u1 of x. Let me denote by this notation. u1 of x integral of phi of x minus y f of y. Okay, and then you have your new y of d sigma of y, and this is d omega. This is called the single layer potential, is called, these are all physically relevant quantities. You see, it's the boundary term, boundary effect of your potential with respect to f. Okay, the single layer potential, single layer potential. Okay, and there is also with the density f, with the density f. Okay, and there is also a double layer potential, which will also you will come across. I may or may not do it. Let's see, double layer potential, which we denote by u2 of x. That's with respect to the derivative, because these are all locally integrable functions, and hence there is no problem. d phi by d nu j. So you are differentiating, this is the normal derivative at x minus y. So this is the boundary values with the nu I coming. This is the grade phi dot nu. So you know that this is equal to grade phi. I can't call it because d phi by d nu j. So I am nu y. So you have to be careful. This is with respect to y I am doing, not nu j. So I am differentiating. This is grade phi dot nu y. Y is to represent that normal is with respect to y. X is a kind of parameter. Like that. D sigma y. This is called the double layer potential. So what is this is a remark, and what is the exercise is exercise. These are all smooth functions, infinity functions. That's because these are all locally integrable, and then y varies on the boundary, and if x is not on the boundary, you can differentiate as many times as you want. So, and this is defined for every x. So u1, u2 belongs to actually very smooth. C infinity of Rn minus d omega. Okay, so that's it. So that's exercise and a remark. So we will come back to the earlier case. So this is the single layer potential. This is a smooth function, and phi is again a locally integrable function. So you see, so now the derivative has gone there. The trouble was there when there is a derivative. You cannot take a differentiation in further differentiation, second differentiation inside. But now there is no derivative here, derivative is taken here. You can take the one more derivative here. So that means you can actually show that the second derivative exists. So if you differentiate, so the I1 and I1 is also differentiable. That's what you are trying to say that. So therefore I1 is indeed different. I1 is differentiable, and by exercise, so you see why that differentiability coming, because there is no derivative now. So inside you have only one derivative to take. Okay, here you can't take the one more derivative to talk about the differentiability. We could do that because of the differentiability of f. So I1 is differentiable, and by exercise I2 is also, I2 equal to U1 is also differentiable. So differentiable, and first derivative is already there. So this will imply your V, the Newtonian potential, is a C2 function. Okay, now of course you have the boundary up to boundary. So you will C or C1, you will have it up to the boundary. So that's not a problem. After the boundary, in first derivative, you can show that. So it remains to show now. So it remains to show minus Laplacian of E equal to F. This requires, so we'll go back, this requires regularization. I will tell you now. Requires regularization because phi has singularity. So I have to do that. Okay, I will do that. And here the exercise has something more. U1, U2 belongs to, and they are also harmonic. That's what Laplacian of U1 equal to Laplacian of U2 equal to 0. Of course, in this space, only then you can do that. So it's all harmonic functions in Rn minus d omega. Okay, so you have some extra things to be done. Okay, so now we have to recall an earlier result. So you have to prove Laplacian minus Laplacian of V equal to F. Choose phi, choose psi, which is a C2 function or C infinity function. C2 is in a CC with a compact support in omega. Why did I choose this one? Then we can show that this is a result which we have actually proved in the PDE1 case. A similar proof you can work it out as we can prove it solves this problem. The convolution of if you take phi with respect to star is equal to psi. Same proof. So you recall from PDE1. So follow the same proof. Recall from PDE1 course or from reference, our reference again PST, our book. So okay, see that if f is in CC of C2 of CC2 of Rn, so we have proved this problem when omega is in Rn. The similar problem, if you work, we have used only two facts. We have not used any property of Rn, whether it is bounded or unbounded, but we have proved that f is in CC2 of Rn. Essentially, f is supported in a bounded compact set. So you use the twice differentiability of, this is a more. So the result we proved in PDE about the existence of solution, with complex support and twice differentiability. What presently we are proving with only C1 of omega bar. No complex support, nor only it is twice differentiable. So that's why, but for this I am choosing as a test function, for which then we have proved that minus Laplacian phi star of f is solves the PDE. This is what we have done. Okay, so we have done this actually in the last class. When you have the same proof instead of Rn, you work. We are not used any special property of Rn or something like that. You need compact support and twice differentiability. With this, now so you choose this function. Now we do a simple computation. So you now compute, because you have to show that Laplacian of v equal to minus f or minus Laplacian v is equal to f. So I act with this is always a trick, omega. Now look at this one. This is compactly supported, so you can take differentiation to other side as many times as possible, because it's twice differentiable, so two times you can take it here. And psi has a compact support, so it will not affect anything. So you will have, and two times you are taking, this will be Laplacian of psi over omega. Now you replace this v, so you have omega, and v is integral over omega phi of x minus y, okay, f of y dy by the definition, and Laplacian of psi of x dx. You apply Fibini theorem, interchange the integrals, everything is in a good condition. So you do this one, so I interchange this interval, so fy will come out, and you will have integral of, this will come out, f will come out, this will come. So x, this also has x, so it will be phi x minus y, okay, Laplacian of psi of x dx of f of y dy. Okay, but this, what is this one? So this is nothing but Laplacian of this is nothing but phi star of Laplacian of psi of x, okay, and f of psi of yeah, this is at y, so you will get because you are integrating with respect to x, so it will be y f of y dy. Okay, but this is psi itself, that's what you say, that you look at here Laplacian of phi, and look, so let me do this one. These are all we have done here. This is same as, because on the convolution it's enough to differentiate on one of them. So this is nothing but Laplace minus phi star of Laplacian of psi, because the differentiation only takes in one of them for the convolution. Okay, so this is nothing but psi of y, so this is equal to integral of psi of y f of y dy. So you now you see that what is the left hand side? Left hand side is Laplacian of v psi over omega. So this is true for, so this is f of y dy. So that immediately implies this is true for all psi in CC2, okay, of omega. That implies Laplacian of v equal to minus Laplace, so there will be a minus sign here. Yeah, there is a minus here, because earlier in this case there is a minus there. So this is minus Laplacian, so therefore minus Laplacian of v is equal to minus f in omega. That's the proof. So that proof is immediate. So there is a fact we are using, and this part we are actually using it, okay, and this requires a proof, which we have done it anyway in our earlier PDE course. Otherwise it's a the regular, sorry, one thing, the regularization is not here right now. We don't need any regularization, so let me move this. Okay, so right now we don't need a regularization. Regularization will come. So we have done when f is continuous. So let's slowly go. F is continuous, result need not be true, but f is C1, the result is true. Now we are going to have an in between what is called a Helder continuous functions. So we are going to define what are Helder continuous functions. Okay, so you want the smoothness not as strong as C1, but then not little more than continuity. Okay, that is provided by Helder continuous function. So I will define that. I will give you the definition, and then we will see why a heuristic argument, why this will work. What is the reason for looking for Helder continuous functions? So the reason is if continuity of f is not enough. This is again I am repeating, many times repeated. Continuity of f is not enough. But differentiability is too much. Differentiability is too restrictive. So therefore, looking for smoothness stronger than continuity, but weaker than C1. That's all I. And I will know how do we look for it, will be motivated to you later. But before that, let me give you a definition of a continuity. Let 0 less than alpha less than 1, and we are always omega bounded open in R. Okay, so you have your definition, Helder continuity. Okay, a function f from omega to R is said to be Helder continuous at x naught, said to be local Helder continuity, uniform, we will define soon, said to be Helder continuous at x naught, Helder continuous at x naught, okay, in omega, if there exists a positive constant such that fx minus fx naught, you would have seen this in a special case already called Lipschitz continuity, less than or equal to constant into mod x minus y power alpha x minus x naught power x minus x naught power alpha for all x. Okay, this is for all x in omega. If alpha equal to 1, this is defined for alpha less than 1, but you can define for alpha equal to 1, then f is known as f is Lipschitz. So you see, so this is something weaker than even Lipschitz in general. Okay, so because when alpha becomes smaller and smaller, this is a weaker quantity because we are more interested in nearby thing. Okay, so when alpha equal to 1, we call it a Lipschitz continuous function. So the typical example we are looking this type of thing. So you see fx equal to mod x power alpha. Okay, then clearly f is Lipschitz of order alpha. Suppose 0 less than alpha less than 1, then f is Helder of order alpha. But it cannot be helder with bigger alpha. So suppose f is helder or say f is helder of order half, then it cannot be helder more than half. Then it cannot be helder in general. I am telling, at least this function helder in general of order, because this has more smoothness, helder of order alpha greater than 1. So for this case, so if you have mod x, so but there is no differentiability here, and you have seen that when you have a Lipschitz continuity, that means fx equal to mod x with alpha equal to 1, and then it is Lipschitz, but still it is not differentiable. But you have already seen in our earlier lectures, when f is Lipschitz, it is differentiable almost everywhere. But for order helder with order alpha with alpha less than 1, you will not get differentiability. Yeah, so more than half I said. It is not 1, it is half. So these are the typical functions of helder continuity. So you need some sort of a growth like mod x power alpha. That's what you are looking. You can control your function with the functions of type mod x power alpha. Okay. So it's definitely little more than the continuous functions, because continuity will not give you any estimate, because it cannot be. So you have other definitions. Uniform Heller continuity definition. Okay, uniform and local Heller continuity. Uniform and local Heller continuity. Heller continuity. F is said to be uniformly continuous in omega. F is said to be uniformly Helder continuous of order alpha in omega if there exists C positive such that modulus of f of x is 1 minus f of y, so it is uniformly united, less than or equal to constant into mod x minus y power alpha. This is true for all xy in omega. And 2, f is said to be locally Helder continuous of order alpha 0 less than alpha less than 1. That's what, of course, alpha equal to 1 also you can define. Helder continuous of order alpha if f is uniformly Helder continuous of order alpha in every compact, not in omega, but in every compact subset of omega. Every compact subset of omega. So that is what is called. So f is uniformly. So if you have a domain omega, so you take anything, so you have the same constant uniformly. So it's each compact set you have the Helder continuity. Then it is called the local, said to be locally Helder continuous if it is this is uniformly Helder continuous. The first one is the definition of a. All right. So now we will denote this one. So notation. Notation is important. These are some important spaces. Notation. So you can take even 0 equal to 0 also get. So it's better alpha. You can also take less than or equal to 1. Okay, so you get Lipschitz continuity. So see, so in general here we take take 0 less than alpha less than 1. Because more stronger when alpha equal to 1. So you denote, so you have the continuity. So yeah, that's a first remark. Every Helder continuous function is continuous. Helder continuous function is continuous, and every f is in, say, C of C1 of omega bar, then f is Helder continuous. So you see, that's just a mean value theorem, right? When it is in C1 of omega bar, then df by dxi is bounded, and you can apply mean value theorem to get estimates. Okay, you can you get Helder continuous. So you, in fact, you get it Lipschitz continuous. That you already proved that Lipschitz continuous. So you have more strong results for that. Okay, so now what we denote C naught. This is to represent continuity. This is to represent the power of omega bar be the space of all. Be the space of all uniformly Helder continuous functions. Helder continuous function. Okay, and then you can make it a Banach space. I will not prove the Banach here. So introduce the norm. Introduce the norm. You denote by norm with 0 alpha if you want, but as no for u in f in C naught of alpha, norm of f in 0 alpha is by definition denoted by, you take its supremum norm, that is the continuous norm, and then it has an extra property, fx minus fy is bounded by x minus y for all x and y, and x not equal to 1. So if you divide this one, this quantity is a bounded quantity by SC, because by definition this one. So you take for all supremum where x not equal to 1. You see, so this is your norm. And what is this? Norm f where? Norm f at 0 is equal to supremum of modulus of f of x, where x not equal where x is in this domain omega bar. So you have that quantity, and then actually this is a Banach space. Okay. C naught of alpha of omega bar is a Banach space. So which I will not prove here. Banach space. Actually, you can define other spaces. In fact, you can define more general higher order Helder spaces. Higher order Helder spaces. Higher order Helder spaces C k alpha. K is an integer where k is a integer 0, 1, 2, 3. You can do so. You look for all functions in ck functions for which that ckth derivative is Helder continuous. Okay, so ck alpha So get familiarized with this before we proceed further. Set of all f in k times continuously differentiable function, but then omega bar. So but then you need the kth derivative, totally kth derivative, d power beta. So let me write it. For d power beta of f is in C0 alpha of omega bar for all mod beta. This is multi-index notation. So these are all the kth derivative or Lipschitz continuous. Okay. And you can define your norm f in k alpha is equal to, so you define the norm, kth norm of that one. So this is the norm k, and then you define summation, you have d power beta of f. Okay, so you are 0 alpha, it's the thing for all mod beta equal to k. So these are all the Helder norms of our order alpha, not infinity, order alpha, and this is all kth norm, right? So what is your kth norm? You can define f at k is all the derivatives supremum of, this is multi-index notation, d for alpha of f of x. Okay, for all mod alpha less than or equal to k, let me not use alpha here, mod beta or gamma, mod gamma less than or equal to k, and for all x in omega bar. Okay, so you have this thing. So this is called the kth order Helder spaces. All these spaces are useful in the study of potential theory and later Schauder theory. So at present I will stop here, and then next week we will continue with the main result which to be proved. Okay, so we will try to understand the derivative. There are two major theorems which will eventually prove the solvability. Okay, thank you.